Alright, so we'll be solving 2017 chemical energies questions. uh, this is the topical paper we'll be solving today. Alright, let's start. The first question is from October November paper 4-2. Alright, the arrangement of the anions around a cation is called the geometry of a cation. In copper, for chloride, the geometry of the copper is tetrahedral and the coordination number of copper is 4. Alright, we know copper is a transition element and chlorine are the ligands. The geometry of a cation in an ionic compound can be predicted from the ratio of the ionic radius of cation and anion involved. So from the ratio of the anionic radius. So now the radius are not given in the data booklet. So if they ask any questions regarding this, they will be provided in the question paper. For now, I'll be using the marking to add the values. So for sodium and for sodium chloride, we have 0.095 over 0.181. As you can guess, this is for upper one is for sodium plus and the lower one is some chlorine negative. It will give us a value of 0.525, and it lies in between in the last section, which is octahedral structure. So it's the octahedral structure, geometry of sodium. Alright, silly me. So the geometry is octahedral, and the coordination number 6. Alright, how can I say the coordination number is 6? Listen, if we have a sodium and if we have water, if we have a sodium and if chlorine is added, right, if chlorines are added, then it will be adding like chlorine, and chlorine is the coordination number. Coordination number মানে হচ্ছে the number of covalent bonds that will be formed. Magnesium chloride. Now if we're dealing with magnesium chloride, it is 0.065 over 0.181. It will give us a value of 0.359, and it lies between this one, so it's tetrahedral, and the coordinate number tetrahedral is a coordinate number 4, right, because it's in the name. Now let's come to the question. Alright, ignore this thing. I was touching my sister there. Now the question states, magnesium chloride is an unstable compound and readily decomposes as shown. So magnesium chloride decomposes into magnesium and magnesium chloride solid. Alright, interesting thing. Use the following data to calculate the enthalpy change of this reaction. So let's start by drawing a Hess cycle. We have 2 magnesium chloride solid forming magnesium solid and Mg chloride solid. Now if you read the question, we have said that we have given the formation of magnesium chloride standard enthalpy change of formation, that means to form 1 mole of MgCl, and also given the standard enthalpy change of formation for magnesium chloride. That makes our life easier. So and formation is 1 mole of compound forms from its elements under standard conditions. So we have magnesium solid and chlorine. We have 2 chlorines with a gas, right, 2 and 2. So over here we'll give an arrow from here because the magnesium and chlorine forms magnesium chloride, and from here. Now for our ease, I will write what's happening over here. Over here we know the enthalpy change of formation for a element is 0. So over here we'll just write enthalpy change of formation of magnesium chloride, and here two enthalpy change of formation of MgCl. This is our del R. Now, as you can understand, as you can see, why I have given 2 over here, because 2 moles of MgCl is being made. So we'll write formation MgCl2 and 2 formation MgCl and del HR. So del HR is formation of MgCl 2 minus 2 formation of MgCl. So we have minus 1642 for this one, then minus we have 2 and the formation is minus 106. This sums up as 42 minus 2 minus 430. Now there's a shortcut. As if you have seen my 2026 solved, you will see that there's a huge shortcut, that if formation given, what we do is that we simply just write the enthalpy changes of products minus reactions for formations. You can also find that, like, see, over here enthalpy change is 0 and over the enthalpy change is minus 642, and the enthalpy change over here is minus 2106. So this is our products, this is our reactants. We can write products minus reactants. You will fetch the same value. See, minus 6.42 minus 2 minus 106. See, it will give us the same of minus 430. The equation for which enthalpy is the lattice energy for MgCl is shown. Del change is the enthalpy change, the lattice energy for the MgCl is shown. Use the equation from the following data. The relevant data from the data booklet to calculate a value for the lattice energy of magnesium chloride. You might find it helpful to construct an energy cycle. Right. So it's a Born-Haber. We have to construct a Born-Haber cycle. We have to construct a Born-Haber cycle. So we'll start with elements first, because we see a MgCl is a one compound, so it must come from its elements formation. So let's start with that. So we'll write magnesium solid, then there's one chlorine, so we'll just give half Cl2 gas. It will form magnesium chloride solid, which is our formation. And you see, ionic lattice energy means one mole of ionic compound is formed from its ions of gaseous state. So we have to make ions that are gaseous. So magnesium can be formed magnesium plus gas. Chlorine will be Cl minus gas. This will be our del H over here, that is del H lattice. And over here it will be our another del H1. Now this del H1 contains few stuff. I'll just write over here. Del H1 contains, we have to turn the magnesium first to magnesium gas. So we will turn magnesium solid to magnesium gas, then magnesium ion, because we need the gaseous ion of magnesium. So it is atomization of magnesium, then we have a magnesium gas, then a first ionization energy of magnesium. Why? Because we are removing an electron. Then for chlorine we have to first atomize the chlorine gas. to form chlorine. Alright, so if you have chlorine gas, we have to make it into chlorine gas, then to chlorine minus gas. Right, how can I do that? Atomization. Now, what is atomization? You can see atomization is the enthalpy change or energy required to form 1 mole of gaseous atom. It's a gaseous atom from its elements. For gaseous particles particularly, it's half the bond energy. That means for one chlorine atom, we'll be needing half its bond energy. Now if we need it for magnesium chloride, if it was magnesium chloride, we would be needing 2 chlorine atoms, so we'll be needing 2 into half bond energies, because it will give us 2 chlorine atoms. All right, atomization. Then we have electron affinity, because we'll be adding an electron to it, so electron affinity. Now let's come now to our answer. Following the cycle, formation del H1 del H. So del H will be del H formation minus del H1, which is for formation minus 106, and then we have del H1. Atomization of magnesium is 147. Then first ionization energy, go to your data booklet and navigate to the page of the ionization energies. Find magnesium. Alright, the first ionization energy is 736 kilojoule per mole. 736. Then we have to atomize the chlorine. For that, we will be needing the half the bond energy. Now go to the bond energy page, find chlorine, that's 242. 242. Then we'll just add the electron affinity, that is minus 349. Let's calculate the values. minus 761 kilojoule per mole. Now suggest how the lattice energies of magnesium chloride and sodium chloride will compare to that of MgCl. Explain your answers. Now you can see that magnesium chloride and magnesium, we can see that chlorine is relatively larger anion, right? So what happens to the overall charge density over here? Over here we have a magnesium plus, over here we have a magnesium 2 plus. So think, which magnesium will have a more higher charge density? Obviously the one, both have the same like ionic radius, but for the sake of charge, magnesium 2 plus is more charged. So you'll write lattice energies compare. So MgCl's lattice energy will be more exothermic. Max Verstappen. Alright, will be more exothermic. Why? Because magnesium 2 plus has greater charge. Also, MgCl2 is relatively larger. So you can actually no need to write for this part. This part is actually sufficient. Now NaCl and MgCl2. NaCl and MgCl. Now you can see this both have a charge plus 1, but there's a catch that Sodium is a smaller ion. Sodium is a smaller ion than magnesium. If you go to your periodic table, you'll find that sodium is in the first row and magnesium is the second. And across the period, your ionic radius increases. So sodium, since sodium is ionic radius of ionic radius of sodium is smaller, it's a greater charge density. Ionic rad ionic radius of sodium is smaller, so it is a greater charge density. Hence more exo. Now, last question. Define the term electron affinity. Electron affinity, you just memorize the thing, right? Electron affinity is the enthalpy change when 1 mole of electron is added to 1 mole of gaseous non-metal atom under standard conditions. But alright, you don't need to write that for now, because say standard affinity, don't write that actually. So the points will be awarded for here is that for 1 mole of electron is added to 1 mole of non-metal atom, and this one. So 1 mole of electron is added and the gaseous part, it's important. Alright, moving on. The table shows standard enthalpy changes of formation for the compounds and ions. Reaction 1 occurs when carbon dioxide is bubbled through an aqueous solution of barium hydroxide. Use the data in the table to calculate the standard enthalpy change for reaction 1. Alright, so barium hydroxide, carbon dioxide, barium carbonate, and water. It makes sense? Does it? Let's go by one. Since we have given ions over here, formation of ions, let's try to divide them. First we'll write we have water, we have barium 2 plus, carbonate 2 minus, carbon dioxide, barium 2 plus, and 2OH minus. So now how are you going to write this? 2 marks, you don't need to write every sheet over there. So we know when formation is given, it will be product minus reactant. So in product we have formation of water. So you can say that formation of water, enthalpy change of formation of water. Alright, let me write formation of water plus enthalpy change of formation of barium carbonate will minus the reactants, that is enthalpy change of formation of barium ion, formation of 2 hydroxide, because there are 2 hydroxide, plus formation of CO2. Then we'll add the values. So here you go. We have water, barium carbonate, barium, 2 hydroxides, and carbon dioxide, giving us the value of minus 110. Let's move on to the next question. If carbon dioxide is bubbled through an aqueous solution of barium hydroxide for a long time, the precipitate barium carbonate dissolves, as shown in reaction 2. The standard enthalpy change for reaction 2 is minus 26 kilojoule mole. Let's see. So barium carbonate or carbon dioxide plus water will form barium hydrogen carbonate. Barium hydrogen carbonate, which has enthalpy change of minus 26. Use this information and the data in the table to calculate the standard enthalpy change of formation of hydrogen carbonate. Similarly, we'll go for the formation method. That in the product side we have uh, uh, hydrogen carbonate. So we have 2 moles, 2 barium, 2 barium iron, 2 barium iron. So enthalpy change of formation of barium, that is 2 plus, oh, sorry, this is my bad, that's 1 barium, 1 barium to formation of hydrogen carbonate minus del HR minus the reactants is enthalpy change of formation of barium carbonate, enthalpy change of formation of CO2, and enthalpy change of formation of water. That's minus 26. What was barium? Barium was minus 538 plus 2 enthalpy change of formation minus barium carbonate was minus 1216 minus CO2 was minus 394 minus water was minus 286. Let's sum this up. Yeah, alright, so it comes down to minus 692. The overall process is shown by reaction 3. Use your answer 2 and the given data in the table to calculate the standard enthalpy change for the reaction 3. Barium hydroxide plus 2 carbon dioxide, so barium hydrogen carbonate. Bro. Alright, let me show a trick. We'll just copy the equation. It won't copy like that, right? My bad. Alright, I'll just take a snap. Oh fuck, I can't take a snap. Alright, oh yeah, I can. So we'll take this equation and put it over here. Let's compare. We'll compare these two equations. So we have 2 barium hydroxides. We have one equation. We have another equation. Barium carbonate 1. Barium carbonate solid plus CO2 plus H2O liquid, giving us barium HCO3 2. For the first one, the enthalpy change was what was the enthalpy change? Minus 110. And for the second one, it's minus 26 for the forward reaction. Alright, so we can say cross out this barium carbonate, then we have a water and water. So the overall equation comes down as barium hydroxide plus 2CO2, giving us barium HCO3 2. So it's just simple addition reaction. So we'll just add this stuff. We'll add these two. Will give us a value of minus 136. Now you can actually do it in a more difficult way, right? You can use it in a more difficult way. You can see the mark scheme, it was more hazardous, but you can use the simple understanding, bro. It's 1 mark, you need to understand this fun. Sorry. How would the value of del HR compare the value of del H4 for the similar reaction with calcium hydroxide as shown in reaction 4? Calcium hydroxide, carbon dioxide, calcium hydrogen carbonate. Alright, that's an interesting question. Guys, what if we remove the metals? Can I do that? Let's try massing them. I am removing barium from this equation and calcium from here. You see, they're the same. The reaction is actually happening between the hydroxides and the carbon dioxide from the hydrogen carbonate. So the metals are getting cut out. The metals are being removed from the equation. So we can say that it will be same. It will be same as the metals that are spectators. And some of you who are more, got a H, you guys can write the equation that 2OH minus plus 2CO2 will form 2HCO3 minus. It's better to write it. I would though. The standard enthalpy change for reaction 1 is Atto, and this is the reason how the standard enthalpy change for reaction 3 might compare with reaction 1. For reaction 3, right? Acha. Reaction 3. And what was the reaction 1? Remind me please. This was our reaction 1. This was our reaction 1. So actually we're saying that reaction 1, the gas is being removed, right? So in both cases gases are being removed, but there's a catch here. Let's think. Max Verstappen, Max. Right, got it. Look, we have, so instead enthalpy change will be enthalpy of product minus enthalpy of reactants. So in this equation we have a solid and liquid. Solids have a very low enthalpy, and then liquids. So you can say solids have an enthalpy of 1, liquids have an enthalpy of 2. Aqueous, since the ions they are more frequent to move, they will have a higher entropy. Given 4. Gaseous on the scale of 10, bro. So you can use the numbers and find your way, but still there's a catch. So theoretically, see, in reaction 1, there's only 1 mole of gas is being removed. In reaction 3, there are 2 moles of gas is being removed. So our entropy of product is decreased more for reactants. So it will be more negative, right? It should be more negative for reaction 3, because entropy of 2 gas, product is less, but entropy of 2 gas is larger. So let's write entropy R3 more negative. Why? because more CO2 is being removed. Pardon my handwriting. Alright, now the question asks, you will find the lattice energy of K2O. But I won't be going into the details. You can just go back in the video and see how I draw the Born-Haber cycle. So I'll be doing it in a shortcut, which is enthalpy change of lattice, enthalpy change of formation minus enthalpy change of 1. This enthalpy change of 1 contains all the stuff that is going on in between, form elements to form gaseous ions. We have formation, which is K2O minus 361. So we have to convert. So we have enthalpy of formula formation, and we have two atomization of K. We have two K's over here, so it's two atomization of K. Then so it's two atomization. Then two fast transition energy. Then we'll have atomization of oxygen. Then we'll have electron affinity. Formation 361, 2 atomization, 2 ionization. What was the ionization energy of K? It's 418. Atomization is half the bond energy. And electron affinity. We have first electron affinity. Right, the two electron affinities. Electron affinity of 1, this makes an O minus. Electron affinity of O minus makes O2 minus. So 798 minus 141. Why 141? Because we are needing this one. It gives a value of 2280. Consider the lattice energy of Na2O would be more negative, less negative, or the same as K2O. Alright, so understand that sodium does in the periodic table. Let's go back to the periodic table. So sodium has a smaller ionic radius. Sodium has a smaller ionic radius. Sodium has a smaller ionic radius, so greater charge density. Hence lattice energy more exothermic. Alright, that's it for today.